This presentation is efficient Gaussian splatting. I presented it at a CVPR workshop earlier this summer and had a few requests for the video, so I'm just recording a fresh version. I'd like to thank some of my teammates at Meta for helping put this together. And a little bit about me. I've been doing efficient AI for quite a few years now, things like SqueezeNet and SqueezeBird and mobile LLM. But I'm relatively new at Gaussian splatting, so I'm kind of sharing what I've learned in the last few months of ramping up in this field and looking at how to make it more efficient. In this talk, I want to help you learn a few things. First of all, just kind of understand all the hype about Gaussian splatting. This idea is everywhere on the internet and at computer vision conferences. I want you to know why it's so popular. I can't promise to make you an expert in just a few minutes, but you'll at least know more than your non-computer graphics friends about GS. And I'll show you a few tricks for speeding up GS that should work on pretty much any device. I want to start this story with NERF. So NERF is a novel view synthesis system that allows you to give it some training images and then view an object from any angle. And it can do simple scenes like this, but also more complicated scenes with nature or with indoor things like Christmas trees. Look at all the complicated details on this that's doing a fairly good job at. Nerf has gotten better over the years. So with Zip Nerf, for instance, they were able to do a whole interior and backyard of a home in lots of detail and view this from lots of camera angles that weren't in the training set. But there is a problem, which is efficiency. So Zip Nerf ran at just a quarter of a frame per second on a large NVIDIA GPU. And one of the flavors of Gaussian splatting called RadSplat does over 700 frames per second on the same type of GPU. And so they get similar quality and similar numerical metrics. And so the reason people are so excited about Gaussian splatting is because it can do many of the things that NERF can do, but at much, much higher frame rate. So in the previous slide, you might complain, well, comparing to zip NERF, that might not be the most efficient implementation of NERF. So in 2022, NVIDIA engineers implemented something called Instant NGP, which is a super optimized version of NERF with lots of clever techniques and custom CUDA kernels, and that ran at 9 FPS on an NVIDIA A6000 GPU. Meanwhile, the first version of Gaussian splatting code that came from the Gaussian splatting authors in 2023 can run at over 100 FPS on the same GPU. So basically, Gaussian splatting, compared to even a very good implementation of NERF, is just an algorithmically much more efficient way of solving the problem. And therefore, we're in the midst of what I like to call the Gaussian splatting revolution. You might see your friends who work on text or natural language kind of redesigning their research and redesigning their products around the assumption that LLMs are here and they make things work better. I'm seeing a lot of people in graphics and kind of at the intersection of graphics and vision use Gaussian splatting to get better results in a modest amount of latency. And so I just came back from CVPR and, at the conference, there are tons of people who were doing NERF last year who are doing Gaussian splatting this year. So Gaussian splats can do lots of things that NERFs could do before, but a lot faster. So for example, there's the Google Street View problem. You might use Google Street View. You go from one scene to the next, it's very jerky. With block NERF, it's able to very smoothly interpolate and do novel view synthesis. With Gaussian splatting, though, you can do the same thing as block NERF, but with real-time, high frame per second interactive kind of latencies. One problem people worked on with NERF and now Gaussian splatting is what they call 4D, so 3D world plus motion. So Gaussian splatting can do a pretty good job with these four-dimensional moving 3D scenes. In this one, the people and the scenes are Gaussian splat, so the environment is Gaussian splat and the people are Gaussian splat. One thing you might notice that looks a little funny is there are no shadows and the lighting doesn't look quite right. So some of my colleagues at Meta have been working on this problem with relightable Gaussian avatars. So here you can see that they can change the lighting perspective and they can change the camera angle and the people can move and everything looks pretty reasonable in the process of doing that. Now I want to give an overview of the algorithm behind Gaussian splatting. I want to start the story with classic computer graphics. So if you watch animated movies or you enjoy playing games, the way those objects in there typically work is there's a mesh that defines the shape. The mesh is a collection of triangles and other polygons. And then there are textures, things like RGB and how to reflect the light and what kind of material that you can overlay onto the mesh to create a realistic 3D object. This is a pretty intuitive representation for artists to create libraries of 3D objects, but it turns out that machine learning struggles to take data and produce accurate meshes and textures. And that's part of why NeRF took off. So the NeRF problem statement is there's a set of calibrated images as input. Typically, you just take a bunch of images of something and then you estimate the camera angle using a technology called Colmap. And then the output is a model that you can view that object from any angle, including novel views that weren't in the training set. More formally, the goal of NeRF is to synthesize all the views in the training set. And the thing that you're optimizing is a small multi-layer perceptron with just a few layers. It has an input camera angle, X, Y, Z, and a couple of rotation parameters. And the output is RGB and then sigma, where sigma is a density term that we're going to talk about later. To get the color of one pixel, we sample the NeRF at several different depths relative to the camera, and then we do what's called alpha blending to combine them together. Part of the intuition of why NeRF is so expensive, for example, why zip NeRF only runs at 0.25 FPS or instant NGP only runs at 9 FPS, is that for every pixel, you have to evaluate your MLP at several different depths. And this leads to, for a reasonably sized image, evaluating the MLP millions of times just to produce one image. So let's be even a little bit more precise about the math in NeRF. I'm not expecting you to memorize this. I'm just showing you because we're going to do something very similar in Gaussian splatting. So the goal here is to produce an output color capital C. And these inputs, these lowercase c's, these lowercase alphas, are information that you're getting from NeRF at each of these depth positions. And so we do what's called blending to combine across all of these to produce the final C. We're blending with a couple of terms. So this T says how much light has already been blocked along this ray. And then alpha is saying how much light is contributed by the current segment of the ray. And so that's how we get the color of one pixel with NeRF. NeRF's been around for a few years now, but before NeRF, there were lots of other ways that people experimented with doing computer graphics. So people looked at mesh and texture, people looked at NeRF, people have looked at lots of different things. But one that's sort of interesting from over 20 years ago is called EWA splatting. Now, similar to what we've seen earlier in this talk, there's a mesh, but instead of a texture, we have these circles, or they're technically ellipsoids. And at the center of the circle is where they're sort of the darkest, where they are the most opaque. And as you move from the center of the circle towards the edge, they become more and more transparent. Their opacity goes down. And it turns out this change in opacity, the way they implemented it in EWA splatting is to use a Gaussian distribution, basically a bell curve. And so this is a bell curve going from the middle out radially in these directions. And you just overlay these circles onto your mesh, and then you can visualize this from any angle, and it's a pretty cool way of doing 3D objects. Now, if we knew this in 2002, and it's such a good idea, why has it just resurfaced recently in Gaussian splatting? So EWA splatting is a lot like Gaussian splatting, but today we know how to train scenes from data, which we weren't so good at doing in 2002 because we didn't have NeRF yet. Today, people use both 2D and 3D Gaussians, depending on the implementation. And now we just have much, much better data sets and much more compute. And so with those changes, EWA splatting kind of becomes Gaussian splatting. So Gaussian splatting is 3D Gaussian blobs floating in space. I only have a 2D screen, but imagine all of these are in 3D. And each of these blobs has a mean or a centroid. And then the variant of the blob kind of going out from the middle is saying kind of how does the opacity drop off? How does it become more transparent as you go away from the middle? So there's also a density. A density is a property of the Gaussian. Density of sort of saying at the middle of the Gaussian, let's sort of look at the opacity. Not exactly, but the gist is the bigger your density, the more opaque the Gaussian will be at its middle. Now, if we want to actually compute the color of a pixel based on some Gaussians, we point our camera at them, we pick a pixel to look at, and we shoot a ray through whatever Gaussians that we can hit. Now, remember we have the same alpha, the same sigma, this roughly the same setup as NERF, but instead of evaluating multi-layer perceptrons at definite predetermined depths, we're just evaluating this function whenever we happen to bump into a Gaussian as we move away from the camera. Now, one thing I want to highlight is this sigma term, that's your density, and this delta is literally how far from the middle of the Gaussian is this ray. So the distance from this black dot to this blue box, that should be your delta. And so if you think about it, this negative term here gets smaller and smaller as you get further away from the center. And what ultimately happens, the further away from the center you are, the less opaque, the more transparent the Gaussian becomes. So that's why as you move away from the middle, it becomes more transparent. And similar to NERF, once you've collected all of these places where your ray intersects Gaussians, you combine them together doing this sum and get your final color. That combination is called alpha blending. Another way to look at this is to think about Gaussian splatting as an overall pipeline. So on the training side, you begin by building point clouds from training images, typically using Colmap. So Colmap both gives you the camera angles and a very rough, a very coarse point cloud based on your training images. You initialize your splats from that point cloud. So all the splats initially start out with the same density, the same size, the same everything. And then you train your Gaussian splats. You just keep complaining about how they're wrong until they start to actually match the training images and reconstruct the training views. Now, once you've done that, that gives you a database of Gaussian splats. So for a very simple object, it might be 5 or 10,000 splats. For say something the scale of an apartment, it might be a couple million splats. And for a very complicated scene, it could be tens of millions of splats. So you take this database and you take a camera angle and you project your splats into the 2D camera angle and you make some covariance matrices for that. Now, covariance matrix might sound kind of complicated, but it turns out if you're trying to look at a multidimensional Gaussian and its geometry, a covariance matrix is a natural data structure to capture that. You then sort Gaussians in XYZ positions and figure out which pixels they align with and what's the relative depth. And then you rasterize Gaussians onto pixels. And roughly speaking, in kind of standard implementations, the majority of the time is this rasterization, and then sorting is maybe 25%, and then constructing covariance matrices and other assorted things is maybe 10 or 15% of the overall runtime on, say, an NVIDIA GPU. Also, the latency is proportional to the number of Gaussians visible in the camera. So if you only have a few Gaussians, this will be much, much faster. If you have lots of Gaussians, it'll be way slower. So that was kind of a textbook introduction. I want to give you now more of a visual introduction of what's going on in Gaussian splatting. Let's say we have 100 images. I'm showing a few of them here of this ficus tree, and I want to be able to view this from any angle, and I want to solve that problem with Gaussian splatting. So I can train a Gaussian splat sort of environment on that, but I'm going to start really simple. I'm going to delete a bunch of the things from the Gaussian splats and just start with something simple. So here's a view of a very simple one. I've taken away lots of things. I've taken away the color. I've taken away the size of the splats. I've taken away the density or the opacity of the splats. You can see even just looking at the splats and making them all the same size and color, it still already kind of looks like the tree. And this is just from training a point cloud and the points kind of move around to be more the shape of the tree. But it's missing some things. It'd be nice to have colors. And one way we could do colors is just to have every splat have one color. Like it could be blue or it could be red or it could be whatever. But that's a little bit wasteful. If you think about it, a lot of times you view an object from different angles and the color changes. So could we have a way of having splats change color depending where you're viewing it from? The way people solve this problem in Gaussian splatting is called spherical harmonics. So imagine you have these different marbles, and each of them has a different pattern of what color is seen from different angles. And then there's some equations that I'm not going to get into here of how you combine these all together. And so the idea is you input a camera viewing position represented as a point on the unit sphere. You put it into a spherical harmonics function where you've trained some spherical harmonics for each Gaussian, and then you get back the color of that Gaussian for that specific viewing angle. And this makes it so you don't need quite as many Gaussians because each of them can solve different problems by being different colors from different camera views. So if I turn on the color and I turn on the density, Now we start to see, if you look at the brown ones on the trunk, as we rotate the tree, they actually, some of them change color. And that's all thanks to the spherical harmonics. You can also see some of them are more see-through than others. That's because we turned on density, and the opacity is kind of based on what we saw in the training set. Now it's still missing some things. They're kind of all the Gaussians are the same size. The leaves look kind of weird. There are big gaps in the flower pot at the bottom. Let's turn on the scale and the rotation. And now it starts to look like the object that we were hoping for. And we can start looking at it from different perspectives, and it all looks right. And the scale and rotation tell us how big each Gaussian should be and what's its three-dimensional rotation relative to some default position. And so to summarize all this, the data structure of one Gaussian splat has these five different ideas in it. So it's a translation, which is your mean, your center of your Gaussian. You've got spherical harmonics, which can be as simple as just saying RGB, or as complicated as if you use, I think it's 3 terms of spherical harmonics gets you a 48-dimensional vector. There's density, which helps you calculate how opaque each Gaussian will be. There's rotation, that's represented as a quaternion. And then finally, there's the scale, which is sort of stretching and warping the Gaussian. And if you think of it as, a statistician would think about Gaussians, you would call the translation the mean and the scale the variance. If you think about it like, just a graphics problem, you can just say, hey, this is the position and this is how it's stretched. So now I want to spend the rest of the talk exploring the question of, can we make this run even faster? And you might at this point say, Forrest, you told me before this thing runs at like 700 some FPS. Like, why would you care about making it faster? So a few reasons. The first is democratization. So sure, you could run at 700 FPS on a server GPU, but on a laptop it's slower, and on the cell phone or mobile device it's even slower than that. I'd like to sort of democratize this and figure out how to make it run fast everywhere. The next thing is run bigger scenes. So I'm expecting people are going to add more and more Gaussians to get more quality. Maybe someday even have billions of Gaussians instead of millions. And we want to figure out how to be ready for that in terms of our algorithm and our implementation. And finally, we need to leave room for other things in the pipeline. Most people don't just want to sit around in a static environment and look at the environment. They want to play a game. They want things to move around. They want to blow stuff up. That all costs GPU time that takes away from Gaussian splatting. So we want to leave room for other things in the pipeline. And it turns out that many ideas from efficient neural network research can actually make Gaussian splatting more efficient. The first example I want to show of this is quantization. So in neural networks, a common thing we do to make them run more efficiently is to quantize them to fewer bits. So instead of 32 bits, we might use 16 or 8 or 4. We can do that here too. So there's this nice study called Compact 3D from some people in UC Davis, and they find that except for the translation, all the other ones can be moved to very low bits. So the translation needs at least 16 bits, but the rotation, scale, variance, spherical harmonics, and density all can be quantized to int8 using a little bit of quantization-aware training. And this makes the model 3.4 times smaller. Now, these researchers didn't try to get a speed up, but I imagine that you could get a pretty significant speed up by doing this quantization, especially speeding up the initial projection of the Gaussians into your 2D scene, because those are loading all of these items into the GPU, or particularly from the GPU's global memory into its caches. And when they did this quantization, there wasn't any kind of degradation in quality, which is great. Another technique is called vector quantization. So I could explain this in complicated terms or general terms, but in this specific case, all I'm really saying is, let's say you have 1,000,000 Gaussians, and each of them has a slightly different 3D shape. The scale sort of stretches it in different sizes. Well, you could have all of these million be unique things, but it turns out if you do some k-means clustering, you can find about 4,000 Gaussians in terms of the scale that pretty much any Gaussian you see in the data will be similar enough to those 4,000 that you can just map it to one of those 4,000, or technically 4096. So you can see here in my toy example, this one, and this one are a similar shape, but all a little bit different. But you could map them all to this kind of vertical oval, and they'll be good enough. That's the intuition of this vector quantization idea. And it turns out you can apply it not just to the scale, but to several of the terms in Gaussian splatting. So this 3D Gaussian splatting with vector quantization also comes from the Compact 3D paper. They do vector quantization on most of the terms. And what they find is they get a little bit of degradation on the MIPNERV 360 data set for their quality, but not too much. And they make it way smaller, 43 times smaller. That's pretty great. And they get a reasonable speed up. It's not huge, but maybe on the order of a factor of two or a little bit better relative to this baseline over here. And so I think probably more speed up may be possible, but again, this compression for the speed up purpose mainly helps with your projection of 3D into 2D Gaussians, and maybe it can help with your spherical harmonics, but doesn't necessarily help with the rasterization process, which is where a lot of the time goes. So I think maybe there's a little more speed up on the table, but I'm not too sure how much. Another technique is pruning. So let's say these are my Gaussians, and you can watch carefully here. I can make some of them go away. Typically, people have heuristics for saying what are the low importance Gaussians. They might try to take the ones that are pretty transparent or very small, or ones that you can't see very often at test time, and try to delete them from the data. Pruning is great. It gives you pretty much a linear speed up. So if you delete half the Gaussians, it should be on the order of 2 times faster. And so you should definitely do pruning if you're not already doing pruning. So one of the studies that does pruning is like Gaussian. They combine it with several other things like vector quantization and distillation, and they actually end up making the quality better than the baseline. I talked to the authors about how they did that. They weren't too clear. They're just, we tried a bunch of things and actually we got better quality scores. And they also make it quite a bit compressed relative to the baseline, but not that much faster. Now, again, I haven't seen a study on purely pruning and what's the FPS improvement, but when I do my own experiments, I see something like a 2x speed up if I delete half the Gaussians, maybe a little less than 2x speed up. Another one I want to highlight is called RadSplat, and they do several things. One of them is kind of improving the training process. So if you think about how we train Gaussian splatting, we only train based on the collection of training images. And, we don't have all the possible views from those training images, but NERF, it turns out, can give you a pretty good geometry, a pretty good estimate of the views from in between your training images. And so what they do is they train a NERF, make that a teacher for the Gaussian splat, and then the Gaussian splat ends up learning something a little bit better than it would have otherwise. That's not really a speed up thing, it's just a cool thing that they did. On the speed up side, they have this thing called the visibility list. And the visibility list sort of says, hey, I don't necessarily need to think about all the Gaussians all the time. And you already ignore these gray ones are the ones I'm ignoring, the blue ones are the ones I'm thinking about, the ones that are kind of outside my field of view. But you might have a wall here, or maybe something that's almost a wall. You can see through a little bit. And these things back here you almost never see. And so the idea with RadSplat, as I say, let's look at 64 common camera angles that we might want to view the scene from. And then let's look at which Gaussians are invisible and which are visible from those camera angles. And when you ask for a new view, it says, okay, let me look up a nearby camera angle and figure out which Gaussians I can ignore safely. And then what you end up with is you get it to run a bit faster because you already kind of delete some of your Gaussians. Another thing you could call this is test time pruning. So during inference time, you're deleting Gaussians based on where you're looking at the scene from. So to kind of summarize what we've seen so far, if this is the baseline here of just the original 3D Gaussian splatting paper on the MIPNERV 360 dataset, quantizing with mostly int8 gets us this improvement here. If we do vector quantization and put everything in int16 and do some pruning, we get 43 times smaller and modest speed up. And if we do light Gaussian, they actually get some better results and they prune a little bit less aggressively. And then finally, RadSplat does several things, but the way they get their speed up, I think, is primarily with pruning and then the visibility list that can ignore certain Gaussians during inference based on your camera view. The RadSplat people also have a version that has over 900 FPS with some slightly worse quality results. So one more thing I want to show is just a little bit on dynamic Gaussian splatting. So far we've just assumed scenes are static, but I showed you a couple demos before where there are people who are moving around. So how does that work? Well, if you have a person, you typically want to train based on a bunch of camera views, sort of just them in a neutral shape without doing any particular expression or any particular body motion. And you train a Gaussian splatting kind of field on that. And then you input, say, you could drive it from a video. So whatever I do, maybe the avatar should mimic that. Or you could say a text prompt. You could ask it to do something specific, using your keyboard. And then you have a neural net that predicts the deltas, basically the offsets relative to the original Gaussians. And there are several papers on this now, but this is the basic idea of how people typically do dynamic Gaussian splatting. And now I want to kind of summarize the overall findings here. So if we care about speeding things up or making them smaller, pretty much everything here except maybe the rad splat visibility filtering have been shown to help with compression of Gaussian splatting. Integer quantization and different types of pruning typically help with speedups. Visibility filtering also helps with speedups. For static Gaussians, dynamic Gaussians is a little bit harder. So we don't yet really know whether vector quantization or pruning works well with dynamic Gaussians because it's changing every scene where the Gaussians are and maybe even what shape they are. So that's kind of, I think, mostly future research to see whether those can give us a speed up. So with that, I hope you found this useful and happy splatting.